Hi everybody, I'm the greatest living inventor, and today we are doing my invention, Lenz's law, navigational deflector. Okay, so I'll write it down. Lenz's law, navigational deflector. Okay, so excuse me, I will take off my jacket. Okay, so protecting spaceship from space rocks with a force field using Lenz's law. Okay, so it sounds like I took the name from what they use in the Enterprise in Star Trek, but of course it doesn't work in the same way. Mine is real, it's physical, and they are like pure science fiction. Okay, so important note, my solution does not help against space weapons like plasma weapons and laser weapons. Okay, I'm saying this because people see on TV the Star Trek and so on, and they think that okay, if it can protect from rocks, I'm sorry, not asteroids but rocks, then it can protect from lasers. So no. Okay, so in parentheses, direct energy weapons, in Wikipedia, direct energy weapons. So I cannot help with this invention, but I can help in this invention against space rocks. Okay, so problem. When a spaceship travels at high speed in space, every stone or rock that's standing in the spaceship's path will puncture a hole through the spaceship. Okay, so if we have the spaceship, okay, and it's flying in this way, and there is some small rock, it will slice through the whole ship. It will go like this and destroy the ship. Okay, because this is like very fast. It travels very fast. The rock is standing, okay, but it's because the spaceship is traveling very fast. It's like the spaceship is standing and the rock is moving in the opposite direction in that great speed. Okay, so we know this. Okay, if you are traveling in Israel, it's relevant. If you are traveling and someone throws a rock from like a bridge or something, then the rock has a lot of energy, not only because of the fall, but because of the car's speed. Okay, so the problem, when a spaceship travels at high speed in space, every stone or rock that's standing in the spaceship's path will puncture a hole through the spaceship. Okay, so bad solutions. Okay, so now I'm talking about other people's ideas and what not to do. So bad solutions. I did it like the good, the bad, and the ugly. So there are bad solutions and ugly and so on. Okay. So bad solutions, and I should say solutions in quote unquote, because it's not even solutions. They don't solve the problem. See question by A. Stoffer and answer by Valorum here. Sci-fi Stack Exchange.com, questions 65052. Why doesn't the Enterprise, okay, from Star Trek, ever hit an asteroid? Star Trek force fields use gravitation. I'm sorry, I will put all the links in the video description, so I'm not writing all the links. I will give you the links in the video description. You can click the links and read for yourself. So, Star Trek force fields use gravitons, which are theoretical particles which we don't yet have. Okay, so yet it's in parentheses and the question mark, because I don't know if we will have ever find the graviton. Okay. In another place, they hint to antiprotons. This suffers from the following difficulties. It's very expensive to make. Humanity so far made only a few nanograms. Okay, I'm talking about antiprotons. Okay, so gravitons let's do it like X. Okay, it's a red X. Can you see the red? Yeah. So gravitons is bad. We don't have them. Antiprotons again, it's bad. We only made so far a few nanograms. But even if we had antimatter available, antimatter and antiprotons are a type of antimatter. So antimatter includes antiprotons. Even if we had antimatter available, it will explode so hard, okay, boom, so hard when it touches the space stone that it will destroy the ship. I'm sorry, I'm just closing the air conditioner. Okay, so it's really, really hot. Okay, but even if we had antimatter available, it will explode so hard when it touches the space stone that it will destroy the ship more than the stone ever would. Okay, so another impossible solution comes from Professor Michio Kaku. Here, thanks to Silly Chip from Daily Motion for this video. Physics of the impossible, how to build a force field. Okay, this is still in the bad solutions, so-called solutions. Physics of the impossible, how to build a force field. I'll give you the link in the description to Daily Motions. Thank you to Silly Chip. Okay, Kaku, Professor Michio Kaku, suggests we use plasma, which is a gas so hot that the electrons separate from the gas atoms that you hold with magnets. One huge problem is, where do you get the energy to heat a gas like that for so long? You need it actually all along the travel. You travel for years in space. Okay, another huge problem, in order to produce the magnetic field that holds the plasma, you need a chamber, closed container, around it, and the space stones will hit this chamber and destroy it. See in Wikipedia about stellarator, the coil. Wikipedia, stellarator, and tokamak. Again, the coil. So Wikipedia, tokamak. Okay, so I'm not writing this because this is like, I will give you the link in the description. I'll just write the names. Okay, so this is another bed solution. Kaku plasma. And the words that you need to look up is stellarator and tokamak. Okay, these are places where you have plasma, but you see that you cannot just put it out in the open. You need to enclose it with something, and the stones will break this something right away. They don't touch the plasma first, they touch the enclosement first. If the rings of the spiral of the coil are not closed but open to the side where the plasma stones are coming. Okay, so this is still in the bed. Okay, this is bed. So if the rings of the spiral of the coil are not closed but open to the side where the space stones are coming, okay, if we have the spaceship and we have a coil and one side of the coil is open. Okay, so it's like we don't need something here to hold the plasma, so the plasma inside will vent into space. We cannot hold the plasma if we don't close the coil, and to close the coil we need something to close it with, like in tokamak. Okay, if the rings of the spiral of the coil are not closed but open to the side where the space stones are coming, we cannot produce the magnetic field to hold the plasma, and it will vent to space. Whatever is here will vent into space. Another huge problem, even though the plasma vaporizes the incoming stone. Sorry, I'll read it again. Another huge problem, even though the plasma vaporizes the incoming stone, the conservation of momentum still means this burning steam of what used to be the stone will hit and penetrate your ship. Okay, so I'll draw it and read it again. If we have the stone, okay, and even if it's a small stone, but let's say this is the stone so you can see it, and let's say it touched the plasma. Let's say the plasma somehow magically don't need to be closed. So now the stone is here, and it's vaporized into particles. Okay, but these particles still have all the momentum. The conservation of momentum means they still are moving, and they will blow up your ship. Okay, So another huge problem, even though the plasma vaporizes the incoming stone, the conservation of momentum still means this burning steam of what used to be the stone will hit and penetrate your ship. Okay, so plasma is a no-go. Next, Kaku talks about lasers, making laser beams crisscross the surface of the spaceship using mirrors. Okay, so we have, instead of a coil now, Professor Michio Kaku says we have lasers here, and here we have a mirror, and here we have a mirror, okay, and here, and lots of mirrors. I'm not painting them, but the laser would move like through all these mirrors, and once the space rock is coming, the laser will fry it, will burn it. Sorry. So next, Kaku talks about lasers, making a laser beam crisscross the surface of the spaceship using mirrors. This suffers from all the above downsides. Energy for the laser, one mirror broken by the first speck, and then the rest are useless. Okay, if this one goes, then all the others just, it doesn't move. The burning steam will still hit the ship. Okay, again, if we have with the laser, and suppose you fried this rock and it's now in a steam, a very hot steam, so it will still continue and hit the ship. Okay, the very hot gravel or whatever it is now, it is, and so on. I'll just drink something. Okay, 17 minutes. Okay, so next, Kaku. Okay, so plasma, and then laser is also bad. We talked about it just now. Next, Kaku talks about physically armoring the spacecraft with nanocarbon tubes. Okay, we talked about it a lot. Nanocarbon tubes, which is also bad. I will explain. With nanocarbon, next Kaku talks about physically armoring the spacecraft with nanocarbon tubes. Today they are very, very expensive and small, but let's say that in the future they are available. It would be like a car accident in an old car that doesn't absorb the energy of the collision. You know, the modern cars are soft and they absorb the energy, and the people inside survive, and the old cars, the car survives, it's very strong, but all the energy is transferred, because it's rigid, it transfers to because the car is so strong, all the energy passes to the passengers and they die. So the vehicle will survive, but it will pass all the energy to the crew, which will die. Kaku illustrates with swinging golf balls into a chain link fencing. But in his metaphor, the fence has posts, okay, like poles, set into the ground, made of steel tubings, This transfers the energy to the ground. In the real case, whatever holds the net in space will not be rigid. That rigid thing that holds the carbon nanotubes in space will transfer the energy of the impact to the spaceship. Okay, we don't have ground there. That rigid thing, if it's soft, it will break. If it's rigid, it will pass all the energy to the passengers and they will die. Okay, so this was all bad solutions. Okay, so I'm erasing this and I will explain now about mediocre solutions. Okay, we can also erase the heading, the title. Okay, so mediocre solution. Which means it's not good, but it's not that bad like the bad solutions. How do Star Trek's deflector shields work? In parentheses, because science with Kyle Hill. Skip to about minute 2:30. Okay, how do Star Trek's deflector shield work? Because science, okay, this is the name of the channel who made it, because it's not the answer, because science with Kyle. He writes it like that, with Kyle Hill. Okay, so and you should skip to minute 2:30. Kyle suggests deflecting incoming things that have electric charge using Lorentz force. Okay, so I'm writing Lorentz force. Okay, it's not what I'm using, but it's in the right direction. Okay, so it's not like this solution is like half good, half bad. Okay, so it's so-so. Kyle suggests deflecting incoming things that have electric charge using Lorentz's force. This idea is mostly good. It solves most of the problems that arise in Kaku's solutions. Kyle doesn't explain what the shape of the spaceship in order to create this field is, so I will assume the best one I can think of for the required magnetic field, a torus, a donut or bagel shape. Okay, we talked about the torus. So let's say we have the spaceship again. Okay, this is it's like the spaceship from Futurama. And we have, I don't have another one in my head, and we have here a torus. Okay? I don't know how to draw it three-dimensionally. You should imagine that the torus is like that. Okay, the hole is here. Okay, I don't know if it's better. I'll just draw it normally, and I hope you understand. Okay, this is the torus. So if you want to enter it, you enter it from here. This enters the torus. The torus is like this, towards you and towards the board, and down and up. Okay, so we have here the rock. And the torus has a magnetic field. Okay, the magnetic field I'm drawing in light blue. So it's like this. They're not supposed to touch each other. Okay, like this. So first of all, if a rock does have some electric charge, let's say this is more, it has an electric charge of, I don't know, like a plus, then it will, I don't remember the physics exactly, but it will be deflected either into this way or the other way. It gets deflected. Okay, so it doesn't hit the ship. So let's say it's moving like this. Okay, the rock will not hit the ship. Okay, torus, donut, or bagel. Okay, the good. Okay, so now we are talking about the good side. There is no impact at all. No hot vapor with enough momentum to penetrate the shield. Okay, remember the red stuff that penetrates anyway, so there is none here. No hot vapor with enough momentum to penetrate the shield, and no stiff, non-absorbing crash. Okay, so this is good. The magnetic field extends outside the ship, so it doesn't suffer from the closed container problem of the plasma. Okay, here there is nothing but field. We don't need a room to enclose it, or some device. Okay, the bed, this has disadvantages, that is why it's not purely good. The bed, where do you get the energy to flow electric current through the torus donut for so long? Okay, we need electric current here to make the magnetic field here. Okay, we don't have so much energy for years. Maybe instead of an electromagnet, we can use a permanent magnet. But then it will be so massive that you cannot accelerate it and decelerate it and decelerate it, let alone fight a planet's gravity. Okay, it's a spaceship. We need to move. This is all on the spaceship, part of the spaceship. Okay, another huge problem that is discussed in the video. I'm sorry, in another video, not in this one, in another video. Oh, no, so it's in this video, so I erased it by mistake. You can just roll back the video and see what was written here. Sorry. So another problem that is discussed in the video, what if they have a neutron bomb? Okay, so so this is a problem. Why is it this was good, but this is bad? Okay, why? What if they had a neutron bomb? Or in other words, the magnetic field doesn't affect objects that don't have an electric charge. If they don't have an electric charge, then this doesn't happen. And this isn't good. Okay? So, not just neutrons. Any object that doesn't have a net charge, because it has roughly as many positive and negative particles. This includes all space rocks. Okay, so most rocks don't have a special charge. They will just pass through this and hit the spaceship. Sorry. Can we put quote unquote electric charge on the incoming object? Okay, we would like to put here, if we could, like shoot from here charges, and this will make this like positive or something, and then it will deflect here. So can we do this? This is a question mark. Can we put electric charge on the incoming object? The ancient Greeks noticed that amber attracted small objects when rubbed with a fur. With fur, like fur of an animal. The Greek word for amber is electron. But even if we can rub off some electrons from the incoming object, it's only on the surface, so that's not enough. Okay, it would be really little. So it's not enough. We can give quote unquote the object, can we, it's a question mark, can we give the object a bigger electric charge? Maybe in the front center of our spaceship we can have an electric rod, like when people do demonstrations with the Tesla coil. Okay, so if you've ever seen a Tesla coil, Let's say there is a coil here. Maybe it will also interrupt the torus electric magnetic charge, but let's say it doesn't. So let's say we have a coil here, like a Tesla coil, and this gives off sparks. Okay, so it has it makes a spark like lightning. Okay, and it shoots any asteroid that comes and electrifies it. That will shoot lightning at whatever is coming. So it's question mark. Can we do this? This will work only if the object is conducting electricity, and even then not always, because if the object is conducting all around, like metal rock, its inside is in a Faraday's cage. Okay, so we cannot penetrate here, even if it's like even if we electrify totally and it's like totally electrified in the outside, but it's not electrified in the inside. So it's not, again, it's not enough charge because of Faraday's cage. Faraday's cage. Okay, so this is no longer a question mark. This is, it doesn't help us. Okay. So I wrote Faraday wrong. Okay, Faraday is very famous. He's like Einstein and Newton. He's in the same level. Okay, so moving on. Just drinking something. 38 minutes almost. Sorry. So maybe if we cannot affect the inside, we can affect the outside. What if we can add to each incoming object something with electric charge? Okay, so the outside. So this doesn't help us. The lightning. But what if we could, and the Tesla coil. But what if we could put much more charge in the outside of the object? Okay, so again, it's maybe it will help us. Sorry. It's not like we have an incoming letter, sorry, and put it in an envelope. These things might come close to the speed of light. So what we need is a very tough cap that will catch it. Okay, so this will not help us because we don't have time to plate it with something. It's coming very, very fast. So what we need, this again is the object, and what we need is basically a cup. Okay, this is like a glass, like I'm drinking from the cup. So this is a cup, just without the handle. Okay, so like a cup that will catch it. This catcher can be made from a strong metal like titanium, which is very expensive, especially considering we cannot collect it back after it's deflected. Okay, so if this is the cap okay, this is the cap. And now the asteroid comes and gets stuck inside here. Okay, so now it's like we coated it. Okay, it gets here, and the whole cup moves to where we want it. Okay, the cup gives it the magnetism, or the electric charge. Sorry. The electric charge that we need. This is the magnetism, and this is the electric charge, and the cap gives it this property. The cap with the asteroid is electric, electrically charged. Sorry. Okay, this catcher can be made from a strong metal like titanium, which is very expensive, especially considering we cannot collect it back after it's deflected. Okay, it goes into space. But we can't just put one little catcher. Okay, this is, I'm calling this catcher. Okay, this is a catcher, this cup. We can't just put one little catcher because we don't know where the incoming object will be. We also don't know what size the incoming object will be. So we end up arranging something that looks like a hierarchy of catchers in layers. Okay, we have a hierarchy catchers in hierarchy. Catchers. Okay, how does it look like? We would have a big catcher, and we would have small catchers. I will erase the catcher because it and we have smaller catchers. Okay, and if a small rock comes, let's say a small rock, then it's stuck in here, and then the whole thing is stuck in here. Okay, if a big rock and if it's strong, it comes. If a bigger rock comes, then it shoves this whole thing, and it will be stuck in here with all the catchers. So a big rock pushes all the catchers. A small rock pushes just one little catcher, or two. Okay, depends on how big the rock is. So this is the hierarchy. Sorry. Okay, can you hear me? Yeah. Okay, what time is it? 45 minutes almost. Okay. So, so we end up arranging something that looks like a hierarchy of catchers in layers. The frontmost layer has many small catchers, the size of drinking glasses on a tray. The next layer has fewer but bigger catchers, the size of buckets. The next layer has even fewer but even bigger catchers, the size of open barrels, and so on. Let's say a tiny meteorite is coming. A tiny meteorite is incoming. It will be catched by one of the cups, and because the spaceship's magnetic field, because of the spaceship's magnetic field, it will be gradually pushed aside away from the spaceship. Okay, so if it's just a little one, then it will be deflected, only the small cup. If it's bigger, it pushes into the bigger cups. Let's say a tiny meteorite is incoming. It will be catched by one of the cups, and because of the spaceship's magnetic field, it will be gradually pushed aside away from the spaceship. This method also has problems of its own. The layers that are far from the magnet far from the torus. The torus is electromagnet. Are in a weak magnetic field, and also a catcher can flip and drop its content, the object, in the direction of the spaceship. Okay, so if we have the cup, and let's say the stone hits not in the center but on the side. Okay, so what happens? The cup might rotate. Okay, remember, nothing holds it, it's in space. So the cup might, even before it makes this, before it deflects, the cup might rotate like this in the other direction. Okay, the stone came from here, rotated the cup. The cup, I still have coffee, so I can't do it, but it's like the cup made like this. And now the stone, which is here, is released and hitting all the spaceship. Okay, so remember, the stone is not magnetic, is not with electric charge, so it can't be deflected alone. It only can be deflected if it's in the cup, which is metal and is with electric charge. The stone itself is not with electric charge. Okay, so this is the problem with this. So also the catcher can flip and drop its content, the object, in the direction of the spaceship. Okay, the ugly. Okay, the bad, the ugly. If the object comes exactly in front of the ring, there will be zero deflection because it will be pulled equally to the left and right, etc., and it will destroy the spaceship. Okay, so another, it's a freak occurrence, but it can happen. I'm erasing the cups just so that make it simpler. Let's say that the stone, this is back to normal. And we have a stone that is coming, but it's coming exactly in the middle of this torus. Okay, so if this is the middle, it's coming exactly in the middle, like dead on the middle. I know it doesn't look like this in my picture, but imagine that I knew how to draw and it's like exactly in the middle, right here. So okay, so what are we going to do? It's pulled with the cup. It enters the cup, but remember it's pushing exactly on the middle. So the cup is deflected towards here and towards here with the same force. So they cancel each other out. So it doesn't get deflected at all. The cup is just continues to come and destroys the ship. Okay, this cancel this, and it destroys the cup with the stone, destroys the ship. It's a freak occurrence, but it can happen. Stone that comes exactly in the middle. So if the object comes exactly in front of the ring, there will be zero deflection because it will be pulled equally to the left and right, etc., and it will destroy the spaceship. This is a low probability scenario, but if it happens, it's catastrophic, like breaking one mirror in the laser scenario we talked about. Okay, so now finally the good solution. But we needed this because we are taking this idea and making it better. Without this force, we use another force. Okay, so now I'm raising this. Now we are talking about the good solution. Okay, so now we are talking about the good solution, which is my invention. My solution uses the catchers system, the cups, but instead of Lorentz force that deflects, I use Lenz's law, which works like in the following two videos by MIT and 60 symbols. Okay, so I'm putting the links in the description. So there are two videos. One is MIT and the other is 60 symbols. So the whole spaceship will be a long tube made of copper. Okay, so the videos are more magnets, 60 symbols. And I will give you the link in the description. And so this is the whole ship is a copper, long tube of copper. Okay, maybe we'll do it in the real color, which is a little reddish. This is pink, but imagine it's like between red and brown, okay? So this is copper. You can also can't see anything. I'll use this one, sorry, it's not exactly the color, but it's close. Okay, this is a long tube made of copper. This is the spaceship. This is in the case of what they explain here. Or the whole spaceship will be a long aluminum tube. This is from a physics demo. So I will do this in black because it's actually gray, but I don't have a gray color. So it's like maybe I use the old marker. Okay, so this is supposed to be gray. Aluminum. Okay, and this is from, sorry, I'll throw you again. And this is a physics demo, Lenz's law, by MIT. Okay. Okay, I don't have the dexterity to make it nice N, but this is N. Okay, like that. So Lenz's law. Dexterity. Okay, so this is by MIT. Okay. So and because of the currents, okay, so now we are talking about Lenz's law. And because of the currents that are induced in the tube, here or here, it will slow down the catcher that contains the incoming object. Okay, so inside the tube, in any case, there is a catcher. Here also a catcher that catches the object. The object comes, enters the tube, enters the catcher, or enters the tube, enters the catcher, and then there are induced currents. Okay, here I'm not throwing everything, just illustrating what happens. I don't know how it looks exactly, but let's say there is induced currents here and here, and it resists what the movement of the bucket or the cup or the catcher. Okay, also here. And these are induced from the movement, from the energy of the catcher. The catcher moves here, so the tube objects. It doesn't want it. It says no. It resists. Okay? So it's automatic and it's free. And because, so we don't, you should see these videos. That's why I'm putting them. And also I'll put them in the description of the video. They show you that the currents are made automatically, like it's passive. We don't have to put energy inside here. The energy of the object that comes and moves the catcher creates these currents by itself. Okay, and because of the currents that are induced in the tube, it will slow down the catcher that contains the incoming object. important difference. Now the catcher doesn't need to have electric charge, but instead the catcher needs to be a magnet. Okay, so now the catcher is a magnet. Okay, and also this. Okay, it's another force. We need to treat it differently. There is another trick. So here the trick is that the catcher is itself a magnet. Not electromagnet, but a magnet, constant magnet. Okay, so now the catcher doesn't need to have electric charge, but instead the catcher needs to be a magnet. For example, neodymium magnets. Okay, neodymium. Oh, sorry, it's one word. Neodymium magnet. Strong fixed magnet. Okay. This method has all the advantages of the Lorentz force method, but doesn't have that method's disadvantages. Okay, so we'll see how much time, 1 hour and 2 minutes, I'll really rush. It doesn't need energy, it's totally passive. We collect the catcher after it slowed down the incoming object, so the catcher's cost is not important because the catcher is recycled. The catcher has no reason to flip because there is no rotation moment, because all the forces act along the same line, which is along the tube, and also the tube can hold it. Like if it wants to rotate, it doesn't let it. And finally, we cannot have friction, but we can have it a longer catcher that cannot rotate. But it also doesn't want to rotate, as I explained. All the forces act along the same line, which is along the tube. And finally, if the object comes exactly in front of the ring, it's still stopped. After the incoming object was slowed down considerably by the Lenz's law, if it didn't stop completely, it is caught by the next layer of catchers. Okay, so here I'm not painting because I have to finish, but it's caught by another catcher here. If it's not, this didn't stop it, there was another catcher here and another catcher here. We can make it really long. Next layer of catchers. We can make the tube very long as long as calculation of worst case scenario will show that is needed. At the back side of the tube, we'll leave and work the crew. Okay, so here in another like a cup, we'll leave and work the crew. Okay, this is the spaceship really. This is all protection. This is the living quarters, this is the work quarters, everything. Okay, after the impact, after each collision with a space rock, the spaceship must reset catchers to their initial location. Okay, so the catcher of the screw need to be moved towards here. The catchers of the stones need to move mechanically towards here, back towards here. to their initial location. I think this means the spaceship has to slow down and stop mechanically mechanically move the catchers back into place. Since the crew move them slowly, there is not a strong force working against the crew. Okay, so there is strong force only when the catchers move fast. The faster the catcher moves, the stronger the resistance. If the crew moves them slowly, there is a little resistance. Okay, by the way, this elongated shiny shape might be the shape of part of the UFO sightings that look like a cigar. Okay, so this is like an idea. Okay, so this was my invention. I hope it was clear, and I'll see you in my next invention. So thank you very much. Goodbye. Thank you.